So we're going to use our graphing calculators. This time we're going to graph what's called a quartic function. So quartic function has a degree 4. So we're going to look at 4 different quartic functions and answer the questions in the table. So first one we're going to graph is the function x to the 4th. So I'm going to pull that up here. So x to the 4th is the first graph that I'm graphing. So it's going to look like this, very similar to our parabola. So what we want to think about, how many distinct factors. So how many times does it touch or cross the x-axis? That would be just once. What is that intercept where it's touching or crossing the x-axis? That would be at x equals 0. Is it tangent to or does it cross it? It's tangent. It just touches the axis, doesn't cross it. How many turning points does the graph have? In this case, it has 1 turning point where it's changing from decreasing to increasing. So let's get back here. How many distinct factors? As 1 distinct factor. The x-intercept is at x equals 0. Its tangent at 0. And it has 1 turning point. So now we're looking at global or local maxes or mins. So we're looking for hills or valleys. So this one doesn't have any maximums. We don't have any hills, but we do have 1 valley, 1 minimum. Now, since it is the lowest value our function ever hits, it is a global minimum. So no max, but 1 global minimum. So that's our x to the 4th graph. Let's graph the next one. So now we have x cubed, x minus 2. So I'm going to stop graphing that one, and I'm going to start graphing that one. Okay, so this time, how many distinct factors does it have? It has 2. Again, that's something you should also be able to tell just by looking at the equation. So what are those intercepts where we're touching or crossing the x-axis? Well, that would be at 0 and at positive 2. Again, you should be able to see that from the equation. Are we tangent to or crossing the axis at the intercepts? Well, it looks like we're crossing at both. How many turning points do we have? So we start decreasing, continue decreasing, and then switch. So we should just have 1 turning point. So let's continue from here. We've got, two distinct factors at x equals 0 and x equals 2. It crosses at both. And it has 1 turning point. So now we're looking for maxes or mins, hills or valleys. Well, we've only got 1 valley, no hills. So again, we have no maximum. We do have a minimum, and it is the lowest value that our function ever hits. So that means it is global. So no max, but does have 1 global minimum. Okay, let's try the next one. So I'm going to stop graphing this equation and start graphing this equation. Okay, so this function is x squared times x minus 2 times x plus 2. So this time we've got 3 distinct factors. We're touching or crossing the x-axis 3 times. Specifically, we're crossing or touching at -2, 0, and positive 2. Again, you should be able to see that just from the equation. So we want to see our tangent. Are we tangent or crossing the x-axis? Looks like we're crossing the x-axis twice and being tangent to it, just touching it once. And how many turning points? So we start out decreasing, change to increasing, so that's 1, increasing, change to decreasing 2, decreasing, change to increasing 3 turning points. 3 turning points. So we've got 3 factors, 0, 2, and -2. It was tangent at 0, and then it crossed at -2 and positive 2. We said that there were 3 turning points. Now, since we said there's 3 turning points, that means there should be a total of 3 maximums and minimums. So let's check. So looking for maximums, we're looking for hills. We've got 1 hill at x is 0. It's not the highest value our function ever hits, so that means it's going to be a local maximum. Looking for minimums, we're looking for valleys. This time we've got 2. They're occurring at they've got the same y value. They're hitting the same low y value there. It does happen to be the lowest value that our function ever hits, so that means it is global. So we've got one local max, and we've got one global minimum, but it happens twice because it hits the same value. It's only one minimum because it's the same value. It just happens to happen twice. So our turning points match up with one local and then our global minimum happening twice. That gets us to the 3 turning points. Okay, last one we're going to graph here. And turn that one off, turn that one on. And I've already graphed this, so I know I'm going to have to change my window size a little bit. So I'm going to change it here, and then we'll look at what our graph is doing. So we take a look at our picture here. So I probably should actually zoom in a little bit. Let's set it back to standard, so you should be able to see them. You've got that low value. We can't actually see it in this graph, but you could see it when it was zoomed out a bit. So checking for how many distinct factors, how many times we touch or cross the x-axis. I see 1, 2, 3, 4 distinct factors. Again, that's something we should be able to recognize from just the equation. We should have 4 factors. What are those 4 factors? Well, we're crossing at -3, -2, 0, and +2. Again, you can see that just from the equation. Are we tangent or crossing? Looks like we're crossing the x-axis each time. How many turning points? So we're decreasing, we change to increasing 1. Then we're increasing, change to decreasing 2. Decreasing, changing to increasing 3. 3 turning points. So how many distinct factors? 4. From our equation, we can see there 0, 2, -2, -3. Crossing all of them. We should have 3 turning points. So checking for maxes and mins. Again, looking for hills and valleys. I see one hill right there around x equals -1. It's not the highest value our function ever takes, so that means it's going to be a local. Looking for minimums, we're looking for valleys. I can see one already, and then the other one we know is going to be below our graph. So the one on the left, that valley on the left, obviously isn't the lowest value our function ever takes, so it's going to be a local, whereas the one on the right is the lowest function our value ever hits, so it's going to be a global. So we'll have one local max, one local minimum, and one global. And again, if we add up the number of max and mins, it should add up to how many turning points we have, and it does. So what does this data tell us? So what determines how many x-intercepts the graph of a polynomial function has in intercept form? Each distinct factor makes one intercept. Each distinct factor makes one intercept. What determines whether the graph in intercept form crosses the x-axis or is tangent? So this is a good time to look at this last one we did. If you notice, in our first equation with x to the 4th and this third one with x squared, we are tangent at 0. Now, if you'll notice, that's because our factors, when our factor was 0, they have an even power. So if your factor has an even power, it's going to be tangent. If your factor has an odd power, then it's going to cross the x-axis. So you look at your intercept, you look at your factor. If it has an odd power, it's going to cross the x-axis. If it has an even power, it's going to be tangent. It's just going to touch the x-axis, but not cross it.